So now that we've defined the normal distribution, let's talk about how we use it. So typically we want to know the probability of x falling between some range of values. Or rather, to make it more general, we should describe the probability of z ranging between two values. But before we get to that, let's save this. Keep that in mind. But an intermediate step that we should do is look at the probability of z being less than all values less than a certain value, that certain value being b. And to do that, we have to integrate from minus infinity to b of our probability density function. And to get that, we get minus infinity to 0. I'm going to break it up into two parts. One before 0, one after 0. And that is equal to 1/2. Again, half of the PDF was to the left of 0, the other half was to the right, so this gives 1/2. This term gives 1/2. And then the second term is the integral from 0 to b of e to the minus z squared over 2 dz. And this is 1 over the square root of 2 pi. Gotta squeeze that in there. This is the 1 over the square root of 2 pi. We have to include that. So let's evaluate this integral. And we'll do that with a u substitution. So we'll say that u squared is equal to z squared over 2, in which case dz is equal to the square root of 2 du. And when we do that, we have the probability of z being less than or equal to b is equal to 1/2 plus 1 over the square root of pi, since we did that u substitution, from 0 to b divided by the square root of 2 of e to the minus u squared du. So it turns out that this integral of e to the minus u squared du it does not have an analytical function. It has to be solved numerically, but luckily it's widely used. So there are many tables, or even FreeMat or MATLAB have a function used to calculate that. And it doesn't calculate that. It actually calculates this: 2 over the square root of pi times the integral from 0 to a over the square root of 2 minus u squared du. And that defines the error function of a over the square root of 2. So this is called the error function. Or ERTH, if you will. But it just describes the solution to this integral. And therefore, the solution to the probability of z being less than or equal to b is simply equal to 1/2 times 1 plus ERTH of b over the square root of 2. Okay, well, I defined ERTH in terms of a, but we're really integrating to b over the square root of 2. So we have to write b over the square root of 2 as the argument in ERTH. Okay, and you can, again, there's tables that you can look this up look up these values, but the ERTH function in MATLAB or FreeMat gives you the integral for this argument. So this tells us how to evaluate b, the probability of z being less than or equal to b. To get back at our original problem, to find out what the probability of z being between 2 points, we just subtract the probability of z being greater than a from the first probability that we evaluated. And that's equal to 1/2 of ERTH b over the square root of 2 minus ERTH a over the square root of 2. So let's look at an example, and we'll return back to the script that I have for you. The first part was the binomial distribution that we looked at, but the second part looks at the probability of a being between, the probability of z being between a and b. So if we run that script, okay, so what this shows is the PDF as a function of z, okay, and right, so again, the probability density function is centered on z equals 0, or x is equal to the mean, and the width of the Gaussian is described by the variance, the standard deviation, sigma. And in normalized z units, the standard deviation is 1. And this is the cumulative probability distribution. So that would be the probability of z being less than or equal to b, and b is varying in that plot. So what that's representing is the area under the probability density function. So as we start from z being -6 to -4, etc., the area is very small. As you can see, the area under the PDF is very small. But as the PDF grows, the area grows, okay, and the rate at which it grows is proportional to the size, the amplitude of the PDF. And at 0, the rate of growth of the cumulative probability distribution starts to decrease as the change in area with z decreases, and it finally reaches or it converges to 1. Okay, so again, that was just the probability. This shows the cumulative probability of z being less than or equal to b. You know what, this should be labeled b here to be consistent with that notation. So I'll change that to b here. Okay, now finally to our answer of the solution we sought, where z is greater than or equal to a or less than or equal to b. Let's just look at a being -1 and b being equal to 1. So the probability of that interval is just 1/2 times the error function of b over the square root of 2 minus the error function of a over the square root of 2. And if we calculate that, the answer is, well, as you can now see, is 0.628. And so that shows the area under the PDF here, and actually it's the value of the it's the difference in the cumulative distribution between 1 and -1. So what we've learned is that for a normal distribution, the probability of x falling within one standard deviation, and let me sketch this out, I guess. There's our axes, and here's our Gaussian, and this is z again, and that's, again, it's centered on 0, so the probability of z lying between -1 and 1 is equal to 68.27%. Okay, and remember z equals plus and minus 1 corresponds to x equaling plus and minus the standard deviation. So one standard deviation encompasses 68.27% of all the points. And you can use that script to show that 2 standard deviations encompasses over 95% of all the possibilities, and going out to 3 standard deviations spans 0.9 over 99% of all possibilities. So remember when we were trying to look for outliers by calculating our z statistics, and we said that the cutoff value was 3, we can see that anything outside of 3, well, I'll just sketch 3 here. Anything outside of 3 is a very improbable value. So we used, in our original example, we used 3 as our cutoff value because we would think that that's very unusual. We have less than a half a percent chance of getting that value in this normal distribution.